Hello, this video is on Sylow theorems. Their formulation, immediate consequences, and one very quick application hinting on the power of these Sylow theorems. We start with a prime divisor of the order of the group. So we have a finite group, and P is a factor in its order. Let's write the order as the maximal power of that prime P, and then everything else. So this everything else is no longer divisible by our prime. A subgroup of the group is called Sylow, or rather Sylow P subgroup. If its order is that maximal power of P. It looks like a very technical concept, very technical definition, but it's going to be, again, very powerful. So the power comes from the three theorems proved by Sylow. The first says that such subgroups exist. For any prime divisor. The second says that if we choose such a prime divisor, then all Sylow P subgroups are conjugates of each other. And the third says that if we count how many such Sylow P subgroup for a given prime P we have, so the number of Sylow P subgroups, let's call this number n sub P, satisfies certain number theoretic condition. Satisfy the congruence mod P. It has to have remainder 1 mod P. So again, statements looking technical, apart from the first, more or less natural one. But let me make a few remarks. The first is just pure logical remark. Third Sylow theorem implies Sylow theorem number 1. Because if that number is of remainder 1 mod P, it cannot be 0. So Sylow P subgroups should exist. But in reality, it's more practical to start proving the first theorem and then deduce the other two. The second remark is the second Sylow theorem imply something about this number of Sylow P subgroups, namely that this number has to be divisor of the order of the group. So first of all, what are we doing here? We're taking a group element and conjugating a subgroup like that with this element. So we are computing all conjugates of elements of the subgroup. That will be subgroup again, because conjugation is an automorphism, and the order will not change under conjugation, because again it is an automorphism. And so we will be acting by conjugation on subgroups of a given order, in particular Sylow P subgroups. And what the second Sylow theorem says is that this action has just one orbit, everything is conjugate to everything else, to anything else. And the size of an orbit has to be divisor of the order of the acting group. And the size is just this number of Sylow p subgroups. And the final remark is the following, which already hints on the hidden power of these Sylow theorems. So if this number of Sylow p subgroups for a certain prime p happens to be 1, then the second Sylow theorem implies that there is just one Sylow p subgroup, and all its conjugates have to be just that subgroup. So the subgroup is normal. Is normal. So I have written normality twice in a symbolic way in the words. And now we could look at the first sort of interesting practical example. The first, in a sense, that it is the smallest number, which is not just a prime, not just the power of a prime, then Sylow theorem will become effectively empty, Sylow theorems, but rather a product of two primes, and the smallest such is 6, the product of 2 and 3. So let's look what Sylow theorems say first about numbers of Sylow 2 and 3 subgroups. The theorem number 2 says that these numbers have to be divisors of the order, and this order, being a product of just two primes, has only 4 divisors, namely 1, 2, 3, and 6. So applying the second theorem first, we have this restriction for the possible number of Sylow 2 and 3 subgroups. The third theorem says that this number has to have remainder 1 modulo the corresponding prime, and in the case of 2 subgroups, it has to be odd. So these are not possible. In the 3 subgroup case, the number has to have remainder 1 modulo 3, and so of course 6 and 3, but 2 as well are forbidden. And we have the situation when we have the unique Sylow subgroup and hence a normal subgroup. So let's call this subgroup T. It has order 3, and by uniqueness it is normal in the group. And as a group itself, T is of order 3, and hence it must be cyclic, so we can choose a generator in it, lowercase t, and then the defining relation for this generator is that the third power is 1. Doesn't matter what we have for the number of Sylow 2 subgroups, we have at least one such. Let's call it S. So we just know that it exists, it is a subgroup, and each such choice, if we have several, will be cyclic of order 2, so we could imagine a non-trivial element in it, the non-trivial element, which is of order 2. So now let's look at what can we say about the whole group. The index of T in the group is 2, because the order of T is 3. And that means that the group has 2 cosets with respect to T, T itself, and the coset of something which is not in T. For example, if we take this little s, it should not be in T because it has order 2. And orders of elements in T are 3 or 1. And so if we generate a coset with this element, it will be something else rather than T. So we will have the complete list of elements in our group. So first elements of T, which are powers of lowercase t of the generator we chose, and then products of these powers with S. And that is, we are already at a stage where we can list all elements. So what is missing, what is remaining to investigate is the product operation, is a group operation, and some of the group operation on these elements is already implicit in, already embedded in the shape of elements. But what is missing, for example, is the answer for S times T. It has to be one of the 6 elements we have. And what do we know about this answer? Just want to stress the fact that if we know this answer, we know everything. Because if we know how to rewrite S times T in the product of T's and S's in that way order, then we know all other possible products. So let's see what do we know about this product. It is an element of the other side coset, but by normality of T, it is the same as the left coset. And hence, S times T has to have a shape of one of the 3. So it has to be the product of some power of T and S. And this power of T has to be something but not 0. Because if it is 0, we have ST equals S, and that is a contradiction. It's just a statement that T is 1, which is not true. So I has to be non-zero, and we have 2 choices, I being 1 or 2. So let's examine them separately. If we're looking at the first choice, we have the relation that ST is equal to TS. And that is effectively saying that our group is abelian. Because powers of S commute among themselves, powers of T commute among themselves, S and T commute, and hence all their powers will commute, and we will have all elements in our group commuting, and the group in this case becomes the product of S and T. And since they are each cyclic groups, we can write it also as a cyclic group of order 6. So that is the first case. The other case is when I is not 1 but 2. Since T has order 3, we can rewrite this equation as T equals T inverse S. So T squared will be the same as T inverse. That is a non-abelian example. The group will be non-abelian because S and T are not commuting. And if we look at what we have for the group, so we have 2 generators, S and T. The defining relations are first coming from their separate cyclic subgroups. Their order relations are like that. And then we have this perturbed commutativity relation, which altogether just reproduces the defining relations and the generators of the dihedral group D3. So what we proved is for a group of order 6, it can have only 2 possibilities. It can be either abelian and then cyclic, or non-abelian and then identifiable with the dihedral group. And in particular, if we take the group S3, which is of order 6 and is non-abelian, so it cannot be this case, it has to be isomorphic to D3, and that is an abstract proof of existence of such isomorphism. Of course, there are more direct proofs using actions of dihedral groups on vertices of the triangle, but this is just an outcome of our classification of groups of order 6, which was possible because of Sylow theorems. So that's it for this sheet. I'll see you later.